Hello and welcome to the latest e-learning event from International Environmental Technology, sponsored by Waters. My name is Rachel Simpson. I am the editor here at IET, and this session will be focused on the utility of municipal wastewater analysis for drug epidemiology, food safety and environmental monitoring, from targeted analysis of biomarkers to non-target screening. Before we start, let me just go over some quick housekeeping. On your display, you will be able to see a questions panel. Please ask questions in this area, and we will review as many as we can at the end with a question and answer session. Any unanswered questions will be answered by email after the session. If you have any questions about or problems with your system, please use the questions box and we will respond to you immediately. Please also ensure that your internet speed is adequate, as wireless connections may disrupt your session. We are making this e-learning event available for on-demand review, and this should be on our website in 24 hours' time. Our guest speaker today is Malcolm Reed. Malcolm is a researcher for the Environmental Chemistry section of the Norwegian Institute for Water Research, NIVA. Malcolm has 15 years of experience in the research, development and implementation of new analytical techniques for the detection of pharmaceuticals, drugs and metabolites in samples from the human population and the environment. Malcolm has in recent years focused on building non-target screening platforms within NIVA. He also has a particular interest in the field of wastewater-based epidemiology, which presents exciting opportunities for monitoring and the evaluation of human health in the environment. So without any further ado, I pass you over to Malcolm Reed.
Good afternoon, everybody, and I'd like to take this opportunity to thank you for registering your interest in this talk. And this field of work, I guess. As you just heard in the intro, I've been working in this field quite a number of years, and it always excites me to see new people turning up to talks or indeed webinars to try and learn something from it. So hopefully today you, the people listening, will get something out of it. You might learn something new with any luck, and with greater luck you won't fall asleep halfway through. Now, just as a brief introduction, you heard that I work for the Norwegian Institute for Water Research. We are based in Oslo, in Norway, although we have a number of offices around the world. And like many other institutes, or we are an environmental institute, but we're actually a non-profit research organisation. And I would like to say that I work in a pristine environment, a little bit like you might be able to see on screen now. That I spend my days out in the wilds collecting samples and improving how pristine the environment is. But like many other environmental institutes, NIVA, or NIVA, NIVA I call it, works often more closely with the human environment. And this is an example on screen now. This is salmon farming off the west coast of Norway. So NIVA's role in this world is to provide unbiased scientific data and guidance for the management of the aqueous environment, so whether that be freshwater or marine environments. So our goal is to help industries thrive and grow, but maintaining a sustainable development. That means we're protecting it for future generations at the same time. So obviously salmon farming is just one example. We work in numerous industries, from oil-related industries, offshore is on screen here. We also work with numerous pharmaceutical industries and production and you name it. But that's probably no different to many other environment institutes around the world. We kind of tend to do similar sorts of things. But the common focus, maybe the industry changes, maybe not everybody's working with oil, but one common feature is that we tend to focus our inputs or our research into the areas where human environments impact the natural environment. So this slide you've got up on screen now is downtown Oslo. It's where NIVA has its head office. So I spend most of my time measuring the impacts of this population on the environment around it. And that's where we come to wastewater, which is where we're talking about today. Many environmental institutes and production facilities, whether it be pharmaceutical or farming, measure wastewater. And for the most part, it's for environmental purposes, so the monitoring, to make sure that the amount of chemicals or substances that they are releasing into the environment are within regulations, or that they are not doing anything that they shouldn't be doing. And that's where NIVA has worked a lot with wastewater over many years, collecting samples from, for example, Oslo here, and making sure that the Oslo municipal sewage system or wastewater system isn't discharging its treated sewage into the fjord or discharging chemicals untreated into the fjord, I should say. But a number of years ago, I think the first publication was in 2001, a very clever gentleman by the name of Christian Dorton at the US EPA began to understand, and he published a paper on it, a position paper, saying that wastewater was much more useful than what we were using for just for pure environmental analysis. He suggested that we would be able to look at it and try to learn things about the community that are connected to it. The basic theory of what we're talking about here is based around the fact that wastewater it reflects everything in society in a way. Everything we eat or drink, take as a medication, everything we put on our bodies or in our bodies is reflected in some way in municipal wastewater and sewage. So the idea is that if we take a representative sample of wastewater from a community, we can analyze that and get a very interesting snapshot about what's going on in that community. And that's where the theory came from. And that's what I'm going to be talking about today, is what we've done so far in that field and where we think it's going to go in the future. I'll start here really with an executive summary. I mentioned at the start, hopefully you don't drop off to sleep, but this is kind of to catch people that do drop off to sleep halfway. This is what I'm going to be talking about. Sewage or municipal wastewater, or whatever you want to call it, whatever term you use, it depends on where you are in the world, I guess. But it's a mixture of endogenous and exogenous biomarkers or chemicals. We can measure those biomarkers in various communities or within one community and start to do comparisons either between communities or over time to start to learn about what's going on and try to understand if there's any correlations between stressors to that community and their overall health. The theory is that we can take a sample of wastewater and try to understand what's going on in the society, whether they're exposed to things or whether they're using things or taking things. A lot of the activities in this field to date have been or coordinated by this SCORE network. At the bottom of the screen you'll see there's a row of logos, a bit like a football team really. I work for NIVA, that's the blue logo at the bottom right, but today I'm kind of representing more the SCORE network in a way. The SCORE network has a website. I encourage anyone to go to it if you are interested in wastewater epidemiology or interested in taking part in some of the activities we carry out. The link is at the top of the page there, you can see. On there we've got some of the publications that we've put out. But essentially the SCORE network is at this stage a relatively small group. We are a European funded group that is we are researchers, institutes, faculties, different people that are working together to try and grow or improve the technique of wastewater epidemiology. We understand as a group that there are numerous challenges associated with this technique. And the SCORE network is there to try and better understand these challenges and also devise ways of improving the results and improving our confidence in the results. Here I've just listed some challenges associated with comparisons between data collected in different regions. Obviously I'll come back to some of this stuff later, but obviously there's no two sewer networks are the same. Sampling procedures vary from place to place because we are often reliant on sampling carried out by wastewater managers or wastewater institute, the actual facilities, their own instrumentation. Analytical techniques obviously vary from country to country and lab to lab, and then obviously population things change. So the SCORE network is there to try and better understand these challenges and also try to work out ways of improving the data that we get. So our approach so far as a network is to put out a consensus document. It's a best practice, a standard operating procedure, if you like, for the collection of samples, analysis of samples, interpretation of results at the end of it, to try and create a uniform platform for people to publish on and produce results. Part of that is a questionnaire which looks at the sewage system that you may or may not be dealing with in your local area. It's a characterization survey. So we're basically looking at trying to better understand the sewage network and what geographical size is it? Is it pumped or not pumped volume? Is it long and skinny? You know, all these sort of things play a huge, have a huge impact on how samples should be collected, for example. So it's a very important part, and I'll come back to some of those issues later. We've created a list of standardized methods that we think are the best in terms of analysis methods, sampling methods. And every year we run an analytical intercalibration or a ring test. I or some of my other colleagues here at NEVA send out samples to many labs every year, and we run this ring test. This year I think it was 35 labs we had involved. So we've sent out samples of wastewater and ordinary drinking water to 35 labs around the world, and requested that everybody analyze those for a set number of compounds and return the results. And that's the sort of thing. We've been running those ring tests for 6 years, I think, now. So again, if you are interested in any of this type of activity, you would like to take part in our ring tests, or would like to pursue some of what I'm talking about today, then please go to the SCORE website. And if you just search for SCORE cost on Google, you'll hit it. And then please take contact with one of us or me directly. So back to the beginning, really. Where did this all come from? And we go back to Christian Dorton's theory about wastewater in 2001, and we've come a long way since then. But the theory that we're talking about here is it relates very closely to drug forensic toxicology, for example. Most people are aware of urine testing, for example, at WADA and the Olympics. The idea being that if a person or an athlete takes a drug or consumes a drug or uses a drug on their skin or whatever, that drug is absorbed into the body, distributed, metabolized, and eventually excreted. So if we take a urine sample from that individual, we can have a good understanding of what that individual has used or taken in the time leading up to that urine sampling. Now, it's a short hop from there to understanding that a municipal wastewater system is effectively a sampling device for the entire population. So what we're looking at is collecting urine from everybody in the entire population at one time. It's a pooled urine sample. We tend to collect 24-hour samples, so it's sort of a pooled composite sample from 24-hour period. And so we can assume that everyone connected to that pipeline, for example, has urinated during that period of time, and we take a sample from there and we can back calculate and have a good understanding of what drugs, for example, people have taken. So we've gone from, on the left-hand side, we've gone from drug testing of individuals to, for example, drug monitoring of the entire population. Now, the benefits of this, and certainly in drug epidemiology, the benefits of this technique are that they are, there's less stigma. We are testing the entire population, so whether a wastewater system has 600,000 people, for example, as it does here in Oslo, I'm testing 600,000 people all in one go. And so the few that, for example, that do take illegal drugs, there's less stigma on them. I'm able to measure their inputs without actually having to go find them directly on the streets, for example, and take urine samples. So we find our results are good in that respect, that there's less stigma. They also capture the entire population in a very, very efficient manner, better than going and trying to collect urine or blood samples from individuals. Or indeed, in many cases, drug epidemiology, often it's not even samples. They're just asking people, what have you taken over the last year, or have you ever used a drug or not used a drug? We don't need to approach individuals. We don't need to ask. We just measure the entire population. And we get around some of the ethical dilemmas that are faced by individual analysis or individual questioning of people that way. So how do we do it? This slide shows sort of a very simplistic 4-step process. It's just the broad framework, and it's a little bit how I'm going to focus the rest of the talk today. It's step one, we collect a sample. It's not as easy as it sounds. We'll come back to that. Step 2 is to analyze the sample. Step 3 is to multiply the measured concentration that you achieved in step 2 by a flow rate, or the amount of sewage that's gone past, which gives you a daily load. It's a mass of, for example, a drug that has gone through that sewage pipeline in a 24-hour period. And then step 4 is we correct that for metabolic processes in the human, and also for the number of people connected to a pipeline, to give a normalized figure that we can then run comparisons across different populations, for example. So that's a very simplistic thing, overview of how we do it, and I'll use that to step through now for the rest of the talk of what we do and how we do. So if we start with sample collection, if you're doing forensic toxicology, collecting a sample from an individual isn't all that difficult. Once you get the go-ahead from that individual, they say yes, they're willing to do it. You can give them a little container and away they go, and you get the sample back. Wastewater collection isn't quite that easy. There's a picture at the bottom. Is actually one of the SCORE members, Erlag, in Switzerland, doing some sampling in one of their sites. I will just mention at this point, the man standing to the left of the picture, his name is Christoph Ort. If you have read anything related to drug epidemiology, or wastewater epidemiology, I should say, in the last 10 years, his name is probably on it, or at least involved in it very heavily. So it's a credit to him in many ways that we've come as far as we have. So Christoph Ort is incredibly important in this field. So he's done a lot of work. He's a sewage engineer, and he's done a lot of work in the sampling side of things to correct our practices in that respect. But what are the problems with collecting wastewater? Well, the biggest challenge is that you're collecting from a large geographic area as a general rule. The picture on the side here is Oslo. The blue is the fjord coming through. There are 2 main wastewater treatment plants in Oslo that service the 1 million or so population that we've got here. And those 2 treatment plants capture an area that is defined by the shaded areas. If you have a look at that map, you've got 2 shaded areas. One is kind of a yellowy color, the other one is a browny, darker beige, certainly on my screen anyway. Those 2 regions are the regions that are serviced by the 2 wastewater treatment plants. To give you a sort of an idea of scale here, the yellower or lighter shaded area, from north to southwest, or from top to bottom, that's around about 35 kilometers. So we're collecting over a very large area. It's 600,000 people in that area, give or take. And we need to try and collect from that area in an efficient manner. One of the biggest problems we've been working on over the years is population, obviously. We need to define the population that is feeding that area. Now, obviously, the yellow shaded area is catchment, but people move in and out of that area over time. So it's not fixed. So we've been spending a lot of time recently working on better ways to understand the population that is supplying our sample, our urine sample, and how much the population varies during that period of time. We've also spent a lot of time defining the boundaries, where we catch and where we don't catch, exactly which pipeline, which streets are connected to one sewage network and which aren't. So we've spent a lot of time with the wastewater treatment bodies, and in this case it's the council, getting that sort of information. It takes time, it really does. So anyone sort of setting out on this field needs to understand these sorts of things, and it's not going to happen overnight. It does take a little bit of time to work into it. Christoph Ort, the person I mentioned before, he created this data a number of years ago. This is related to flow, or the flow of sewage through a network. Our goal in collecting samples is to try and collect a 24-hour composite sample. That means that we collect a sample, lots of small samples, say every 10 minutes over a 24-hour period, and pool all those 10-minute samples into one large volume. and we need to do that in a statistically correct manner, or an accurate manner. So in doing that, we need to understand the flow characteristics behind the network. So the upper left A plot, across the x-axis you have time. It's a 24-hour period, so 8 a.m. to 8 a.m. the day after. And the flow is represented in the y-axis. And you can see that in the morning, earlier morning, you get a peak. And this is related to diurnal effects. So people waking up in the morning, going to the toilet, having a shower, turning dishwashers on, all that kind of thing. And then heading off to work. And you get sort of it tapers off in a plateau for most of the waking hours of the day. And then at night, say from 12 a.m. to 4 a.m., you see a drop. And that's when people are often asleep. And so the flow drops off. Also industry, if it's feeding into the wastewater system, is maybe slowing down at those times. So shift work goes off, shift work, and production goes down. So that's A is kind of your typical flow, and that's a gravity fed. That means it's just whatever's being put into the pipe is coming out at the other end, and that's kind of a good representative of the average situation. Plot B is if you have a large capacity in the pipe, and basically effectively that's averaging out the entire system. So your things get smoothed out over time. And that makes sometimes sampling a little bit easier. Plot C is pumped system. That means that there's always the only time there is flow in the wastewater treatment system or in the pipes is if pumps are running. And so in this case, you can see lots of spikes up and down, up and down, and up and down. And that's just the pumps turning on and off, or adjusting flow. So this, we have to be very aware of this if we're designing a sample collection scheme here, because if we sort of go and collect a sample at an incorrect time, it might be that there's actually no flow going underneath us at that point, and we're just collecting a static, something that's been there for a few minutes or a few hours even. And then plot D is a mixture of gravity and pump. So the point I'm making here is that there's very different flow characteristics in every different wastewater system, and we have to understand that. And that's what the SCORE network is trying to help people do, is understand that there are different characteristics, and that we can design sampling strategies that are most efficient for the characteristics that you've got in your own particular sewer. And this gets back to, this next slide is again back to Christoph Ort's paper, and it suggests what sampling strategy you should or shouldn't use. We tend to want flow proportional, volume proportional. What that means is the greater the flow, the more sample you take. If there's no flow, if it's a pump system and there's no flow and it's turned off, then there's no point collecting a sample at that time, because it's going to be meaningless really. But I encourage people, like I said, this presentation will be live or available later on. So if you need these references, I encourage you to write them down and go get them and have a read. They are quite important. So we'll assume that we've collected our sample, that we've followed the guidelines by SCORE or other people looking into this, and you've got yourself a representative sample of wastewater. We then go and analyze it. How do we analyze these samples? Well, this goes back to our analogy with forensic toxicology, urine analysis. And it follows very clearly, actually. I mean, if we, in wastewater analysis, tend to use exactly the same techniques as used in the hospitals for forensic toxicology, or indeed WADA for the anti-doping. I have the same analytical instrumentation, and we use roughly the same techniques. Basically, we collect a sample, and then we pre-concentrate that sample via solid phase extraction most often. And then we run LCMS or GCMS analysis on that. It's very, very similar to forensic toxicology in that respect. And like forensic toxicology, we don't always focus ourselves on the parent compound. This here is showing a slide of some of the narcotics or illicit drugs and just recreational drugs that we measure on a regular basis. So I've got cocaine, amphetamines, cannabis, ecstasy. I've also got nicotine in there as well from cigarettes. We might not necessarily measure these parent compounds because measuring those compounds in wastewater doesn't necessarily prove that they've been used. And what we're doing in wastewater epidemiology is we're trying to measure how much people have used or taken. So with that, we have to measure the urinary metabolites. exactly the same as they do in forensic toxicology, really. And we use the same markers, the same urinary metabolites that are used in forensic toxicology, exactly the same compounds. And we use the same LC-MS transitions as they use. It's exactly the same. So this plot is for ethanol, actually, from alcohol. In the middle of the plot, you see ethanol, and moving upwards, you'll see excretion of that ethanol unchanged. So it's excreted in trace amounts in sweat. About 2 to 3% of ethanol that you drink is excreted unchanged in urine, and you get around about the same proportion in breath, and it's the breath that you get caught out on breathalyzers, for example. Moving down underneath the ethanol is metabolism, and it's here that we focus our efforts in wastewater, and indeed in forensic toxicology they do the same. So they're looking at measuring the amount of the metabolites in urine. They are very small amounts compared to the total amount of alcohol that has been consumed, but they're consistent, and these amounts are known. So what we do is we go and we measure, in the case of alcohol, we measure ethyl sulfate. So we measure that in wastewater, and we can then back calculate how much alcohol has been consumed in the community, and quite accurately. The next example is cocaine. Again, we could measure cocaine itself in wastewater. But this might just be related to disposal, people dumping it down the toilet, or it's wasted. So it's not proving that someone's actually used it. So again, we tend to measure the urinary metabolites. In this case, benzalkonium is the most common one. And that we have a greater confidence that the drug has been used. So a little bit more on sample preparation, for example, analysis techniques. This is a picture of me and one of my colleagues at NEVA. This was a number of years ago, and you can see what I'm dealing with there is a very large volume of water, and I'm trying there to load it onto around about 20 SPE cartridges, Oasis HLB. That is extremely time-consuming, laborious, and error-prone. So people that work in wastewater may not be well, this may actually be a relatively familiar sight for some people that are working in wastewater. It tends to be large volumes, and it's very time-consuming per sample. Obviously, you've got to ship these large volumes around the place and store them at huge expense. So I've been working over the recent years to minimize volumes as best I can to improve efficiency and to reduce costs a lot. So one of the ways that I've been doing that is moving to 96 well plates. This slide at the top in the blue flow, you've got traditional methods, and the volumes and the methods I'm using here or used as an explanation here are pretty much the average that I see for most wastewater epidemiology papers. If you look at the literature, there's a couple of hundred papers now on this field. They tend to all use around about the 50 to 500 mil wastewater sample mark, roughly. So relatively large volumes, not horrendous. 500 mil samples isn't too bad. They are loaded onto SPE cartridges, solid phase extraction cartridges. By the vast majority are Oasis MCX cartridges, so that's a cation exchange cartridge for bases, so it's the basic drugs, and they work very, very well for that. There's also a growing use in Oasis HLB purely because of the non-target screening work, which I might mention a little bit later. But generally, it's cartridges. They tend to be the 6 mil cartridges with, say, 100 or 250 milligram absorbent. So we'll load, say, 100 mil of wastewater onto that. We then wash and elute the SPE with normally 2 or 3 column volumes. So that could be upwards of 10, 15 mils in some cases to elute these compounds, to elute the compounds and get them off. The problem with that then, of course, is then we have 15 mils, say, or 10 mils of a solvent, which is incompatible with LC-MS. So we have to dry that down and then reconstitute that. And typically people reconstitute in 500 microliters of an aqueous phase that can go on to, for example, an LC-MS. If you run a UPLC system like I do, then you'll be injecting somewhere like 5 microliters of that. And I've said that it has to be roughly 15% organic, but it has to be roughly closer to your starting conditions of your gradient, sort of standard rules for LCMS, I guess, or LC. Problem with that, if you look at that entire blue trace, or from left to right, the efficiency isn't great. You've injected, at the end, 5 microliters out of 500, so 1/100th of your sample. So effectively, on the column, the LC column, we've really only taken a 1 ml water sample, or wastewater sample. So it's a pretty inefficient way of doing it. So I've started to look at the red trace along the bottom. So I start with a 2 ml wastewater sample. I load that onto a 96 well plate, Oasis HLB micro extraction plate. So 2 mils is more than enough. Because it's a micro extraction plate, the volume or the mass of absorbent is obviously tiny by compared to the cartridges. So it requires less volume to elute. So I elute in only 150 microliters. That way I don't need to do a dry down step, and I don't need to do any reconstitution. I just inject straight organic, and I inject 50 microliters straight onto the LC column. Now, many will instantly say, well, hold on, I had to reconstitute 15% organic for the blue. Why don't I have to reconstitute or dilute the red? And this is one of the tricks that I'm using, or one of the modifications that I've made to my system here. And I'll talk about that now. A traditional high pressure mixing LC system, like an Acuity UPLC, has an aqueous phase and an organic phase, a phase A and a phase B, for example. They go through a mixer, which is shown in green. After the mixer, you'll have the loop, which is where the sample is introduced, and then it goes from there onto the LC column and then to the detector. That's sort of fairly standard. Hopefully that's not too unfamiliar for most people running certainly high pressure mixing systems. At the bottom is the modification that I've made to our system here at NEVA. This is a 5-minute modification when you know how to do it. Literally, it takes 5 minutes. All it costs is a piece of tubing. So it's about the cheapest modification you could ever do to an LC system. Literally, I just move, put a slightly longer tube in, and effectively what that does is it moves where the loop is placed in the flow path. So if you look in the bottom plot there, you can see that the loop and where the sample is introduced is now on the organic flow before the mixer. The benefit of this is that my sample doesn't need to be an aqueous, made up in an aqueous mobile phase anymore. It can be in anything. I've even injected immiscible solvents, 50 microliters of, onto an LC system and got it to work perfectly here. Because what you're doing here is basically introducing your sample as part of the organic phase. It's mixed in with the aqueous phase and then loads onto the column, or it's focused on the column. I believe in proteomics they call this similar sorts of things to this as that column dilution. In this field, I tend to call it post-column or post-loop mixing, I should say. It is extremely efficient. So I now inject between 50 and 100 microliters of 100% organic straight onto aqueous LC and get incredibly sharp peaks and obviously increases sensitivity. So what I'm getting out of this is moving from large volumes where I need, liters to get detection. Now I only need 2 mils to get down to low nanogram per liter detection limits on a triple quart LCMS. The benefit of the 96 well plate obviously is also that it's much quicker, so I can do high throughput methods. So I can easily do 100 samples in a day, whereas the old method I really would have struggled with many more than 20 in a day. So we've really gone for this in a big way. So I encourage people to look at it if it's possible on your system. Certainly contact me if you want help in doing it. Like I say, it's a 5-minute job if you know how to do it. It's not a big modification. So next thing, what can we show from this technique? Well, obviously, I've talked about the potential. Here we have cocaine data from Oslo. So what you can see on this plot is some data from the Oslo treatment plant over a month, September 1st to September 30th, and it's cocaine. And the first thing that you see at the start is 2 peaks that pop up at the start above September 1st. They are Friday and Saturday nights. Sunday disappears under Saturday, and then you have a a low sort of heart rhythm along the bottom of the screen there, which is the Monday to Thursday, and then you get another peak of Friday and Saturday. So in that plot there, you can see 4 Friday and Saturday cycles, and those 4 Friday and Saturdays are the big peaks that come out. What this is telling us is that cocaine is used mostly at the weekend. It's a recreational drug, and the majority of the total amount of cocaine used is used at the weekend. That is certainly similar to what you see for alcohol, and this is alcohol at the same time in the same samples. So we see, again, increased use of alcohol at the weekends, probably not surprising. And although you see here that the hop over the weekends isn't as high as it is for cocaine, and that's because people tend to use alcohol during the week as well. So we're not restricted just Friday and Saturday. The last plot we see here now is for methamphetamine. Methamphetamine tends to be more of a habitual heavy drug user drug, certainly in Norway. So people that use it all the time. They don't save it for the weekends. They are addicted and they need to use it. And you can see that that's kind of reflected in this plot for methamphetamine. It's a bit erratic. There's hops and bounds all over the place, but you lose the clear weekend spikes that we saw for alcohol and cocaine. What else can we see? This is data from SCORE. This data, at the top of the screen there on the left, you can see the website. SCORE reports to the European Monitoring Centre for Drug and Drug Addiction annually, and all our data is available online, and it's really cool. You go to that website and it's all fully interactive. There's maps and plots and charts, and you can do all sorts of wonderful things with the data if you want to. So I encourage people to go there and have a look and have a play at what we've done. This slide is actually old now. We've obviously got data through to now as well, 2016. So please, I encourage you to go have a look. But what I wanted to show you here was this is cocaine. So it's green. If you look at the top screen, it's highlighted green. It's cocaine. So the bigger the circle, the greater the use of cocaine in a region. So this is 2012, and then if I hop to 2013, and then 2014, you can see what's going on. We're doing this every year, and these are the sorts of plots that we're generating. What you may have noticed, if your geography is any good, there's a line through Germany and Denmark, all the way down to Italy in a way. It's sort of a diagonal line going from northwest to southeast. Southwest, so in France and Spain, for example, and the UK, we have higher rates of cocaine use than we do, for example, up in the Nordics, northeast and Central Europe. There's a very definite line that is always there. It's a common feature for cocaine. It just says that there's greater use of the drug in south and west of Europe. This is in very stark contrast to amphetamines. Amphetamines are the opposite. So this is methamphetamine for 2012. You can see that the use is higher in the northeast sector, or sort of central and eastern Europe, than it is in west and south Europe. The 2012 data, we have 2013 data. There's some big lumps in the middle there. They were actually mostly to do with Czech Republic and eastern sides, wings of Germany, I suppose. And then 2014. One thing you'll notice is that we move from year to year, the cities that we have change, and that's just because we're doing this for free. Everyone supplies us data where they can, so it's completely voluntary in a way. So we're lucky to get what we get from this. We're up to, I think, 60 cities now at the moment, between 60 and 70 cities that we do on an annual basis. That's pretty good for free work. The last one I just wanted to show you was for cannabis. This is the cannabis metabolite, and there's fewer cities measuring this because it's actually much more difficult to analyze than wastewater. But what this is showing you is that we don't get that east-west, north-south divide. It tends to be more uniform. Wherever you measure, it tends to be roughly similar levels, and that's saying that cannabis is more uniformly used throughout Europe than, say, some of the other drugs are. So this is the sort of data that we're generating, and we're reporting to the European monitoring centres. And this is sort of the starting point of where we want to go forward with this technique. We want to move this on and go to other things further than just drugs. The next slide is just to show you our worldwide coverage so far. We're growing, so I encourage you, if you are interested in taking part in this activity, then go to the SCORE website or take contact with one of us, and we encourage you to to join. It'll be good to see. So where else can we go with this? Well, Kevin Thomas, who works at NEVA, and I published a paper a number of years ago, which was just a theory paper really, where we tried to guess where this technique might go. And one of the things that we said was that we could measure community response to a stressor. So here we have a blue line, which is the measure of a antihistamine, cetirizine, in wastewater, and then the coloured bars are the pollen outbreaks related to grasses, for example, hazel and that kind of thing. And again, it's quite obvious to see it. It's the summer months. It's a 13-month period from December one year to December the following year. You see that the pollen outbreaks occur over summer months, and we see a huge rise in the amount of this antihistamine used during that time. So this is very encouraging for this technique as a proof of concept that an environmental stressor can be measured in some way in wastewater, in this case just an antihistamine, but it's sort of proof of concept. So in that paper, Kevin Thomas and I sort of postulated a number of things that we could use wastewater-based epidemiology for. Everything from lifestyle, which I've talked about, for drugs and alcohol, for example. But going on to nutrition, we can look at flavonoids, for example, urinary sugars, that kind of thing, to try and understand what people are eating and drinking, and if there's any correlations between what people are eating and drinking and their health outcomes in that community. That takes us to the next one down, which is health outcomes, and measuring cancer biomarkers, for example, was postulated. And I'll come back to one of these oxidative stress biomarkers in a minute. That's a really good example. And then the final one at the bottom there is environmental stresses, so measuring toxins or measures of toxins. But if we go back to the health biomarkers, that's where some of the work has started to happen now. One of the researchers here at NEVA has actually done some work on isoprostanes. Isoprostanes are a measure for a human body's ability to detoxify itself. That's a very simplistic way of putting it. But if your body is maybe not keeping up with detoxifying things, then you produce isoprostanes. Again, very oversimplistic explanation, but the idea is that the more toxins you have, potentially the more isoprostanes you produce. And they're excreted in urine, and they correlate very well in urine. And what this plot is showing you is a relationship between cotinine and hydroxycotinine. They are nicotine metabolites, so from smoking and cigarettes and that kind of thing, correlating that with isoprostanes in wastewater. Both these measures in wastewater. And you can see it's a bit of a scatter, but there is some degree of correlation there. So this is encouraging for us going forward. We think this is excellent in terms of going forward with this technique, that we can measure, for example, an isoprostane and try to understand what is causing that. Obviously, hydroxycotinine and nicotine aren't the only source of toxins in the human body, so that's part of the reason why there's a lot of scatter there. But we just wanted to show that this does have some potential for future. So what else do we measure in wastewater? One of the other SCORE network members, Mario Negri in Italy, in Milan, they published relatively recently some work on pesticides. And the graphical abstract on the bottom right-hand side captures it in a way. The theory is that we eat fruit and vegetables. The fruit and vegetables have residues of pesticides in or on them. We metabolize those, excrete them in urine. We can take a sample of wastewater from a community, analyze that, and try to understand the community level exposure to those pesticides. So again, it's just going back to toxicology on individuals. It's known that these pesticide metabolites can be measured in urine of individuals. We're just moving that to the entire population. So I've just taken a snapshot of that data, because it's not mine. This is SCORE data, as I say, from Mario Negri. But they collected samples of wastewater from all over Italy and analysed them for a vast array of urinary metabolites of pesticides, mostly organophosphate pesticides, and then are starting to correlate that with urine data and also with usage data, and also to do with where these pesticides may be applied. So it's not just dietary intake, but say airborne intake as well. So here we see some of the things that they're picking up. The they're picking the water concentrations are in the, say, 20 to 300 nanogram per litre level. So they're actually quite reasonable concentrations. They're certainly not low. They're easy to detect, easy to measure. And so they're moving forward with this and trying to use this technique to better understand or provide a way of measuring an entire community's exposure to pesticides rather than taking individual samples. We'll just sort of head back to the executive summary at this point. I just wanted to explain where we've been and what I've sort of tried to introduce very rapidly. That sewage is a very useful thing. It's better than just environmental analysis. We're starting to use this for a lot. We believe this has huge potential for epidemiological measures, early warning systems, for example, and trying to better understand community exposure to toxins, for example, or health outcomes. There are a number of challenges, however, that we're working on and a number of limitations with this. The biggest limitation, obviously, is that we're looking at the population as a whole. We're not looking at individuals. So we lose some of the information related to individual, what an individual person may or may not be exposed to. We're looking at huge populations, so sometimes it's hard to actually draw the correlations that we need to draw. There are obviously problems with exogenous interference. So the pesticides is a good example. I can measure a pesticide metabolite, but it may be related not only to human consumption, but it might have been related to airborne contamination or from spraying in an area, for example. We also see large variability in some of the data, and we see issues with the stability of some markers. I mean, the theory is that we could measure everything. Anything that a hospital can measure in your urine, we could measure in wastewater. And the truth is, unfortunately, that we can't. Wastewater is a very aggressive environment, and so many things break down very quickly. Stability is difficult in forensic toxicology, but it's extremely difficult in wastewater analysis. So many of the things we just cannot measure because they disappear too quickly. The last two challenges are related to the analysis, and this is to do with concentrations often. We tend to say that wastewater is made up of around about 1% urine on average, depending on where you are in the world. But the rest of it is wastewater, is shower water, washing water, rain if it's influenced by that, industry, that kind of thing. So wastewater is a very small percentage of actual urine. So it can be challenging, some of the analytical techniques here. But we're working on it as a group. SCORE is trying to get it ironed out. And I'd very much encourage your input. If you'd like to join us or be part of the network, then I would like to help out, then I would very much encourage you to do so. I finish on the acknowledgement slide. This is an EU, SCORE is an EU funded thing. So by law, I have to acknowledge that it is EU funded, and I very much appreciate the EU is actually taking an interest in us and trying to get this technology going forward. So at that point, I'd like to thank you for listening and thank you for your attention. And hopefully, if you have any questions and we don't answer them now, please feel free to contact me by email or send them later, and I'll answer them directly afterwards.
Well, Malcolm, thank you very much for that very interesting presentation. You've got a wonderful job, and one I think that many laboratory-bound audience members would be quite jealous of. Now, we have some questions that we do have time to go over. As I said earlier, we may not be able to go over all of the questions that we have, so I'll take this opportunity to remind everyone that unanswered questions will be answered via email when this e-learning event is finished. So Malcolm, our first question: how do you ensure homogeneity of samples and avoid thermal and gravitational stratification effects?
A lot of that comes back to Christoph Ort's paper in terms of the sample design. Wastewater systems tend to be very turbulent, particularly municipal wastewater systems. There's a lot of movement going along. There's a lot of mixing. The one in Oslo, for example, the flow is 3,500 litres a second. So it's equivalent to a river, really, in many cases. It's a river of sewage running underneath the city. can be very turbulent, so we get a lot of mixing. So in terms of stratification, we see a lot of mixing. In terms of trying to get a representative sample from that flow, that's where we have to very much rely on some of the advice of Christoph Ort. The sampling is done relatively rapidly, so we actually have automated machines drawing samples at a maximum of 10-minute intervals, and they are just small volumes. And those 10-minute intervals, a small volume is drawn up and drawn into a refrigerated sampling unit, and we collect for 24 hours, and that is one pooled 24-hour sample. So we have 10-minute intervals, so 6 per hour, times that by 24 hours, and that becomes one sample. The volume that is drawn at any one time is proportional to the volume that is flowing past the pipe at that particular time. So they're connected up to flow meters on the sewage system. If we don't have the flow meters connected directly, then we just increase the rate at which we're taking samples. So we can draw samples very, very rapidly to try and increase the accuracy of the sample. Obviously, what we're trying to do here is decrease sampling error. And that is one of the largest sources of uncertainty in this technique is sample uncertainty. So we're trying to work on that all the time. That's one of our greatest focal areas, and that's why this questionnaire that Christoph Ort designed for sewage characterization is so important. We need to understand the sewage characteristics, design the most appropriate sampling system in that location. So hopefully that answers the question.
Thank you very much, Malcolm. Now, the techniques that you're discussing, have they ever been used to test DNA from viruses or bacteria?
Yes, they have. We had somebody here at NEBA working that for a while. They can and they do. I haven't been directly related with much of that work in the last 6 months. But SCORE actually has a working group looking directly at that. It's not my field, unfortunately, viruses and DNA. I tend to be more drug focused. But yes, it can and does work. They're developing sensors for that purpose as well within that field. I unfortunately can't answer directly. However, if you would like more information on that particular field, then I'd encourage you to email me, and I'll forward that email to the person responsible in the SCORE network.
And does rainwater ever affect the results of the analytical techniques that you're using?
Yes and no. The simple answer is no, it doesn't. All the data we generate, we normalize based on population, we normalize on flow. Part of the analytical technique is you measure the sample and then you multiply that by the flow that has gone through the sewage treatment plant. What does happen though is if you have a lot of rain, a huge rain event, then you're effectively diluting the urine out a lot. So that can affect your detection limits. So sometimes something might drop below the detection limits purely because there's been so much rain, or snow melting, as in case of Norway. That's really the biggest impact. It doesn't affect the quantification in any way because we normalize for flow. The other negative impact of flow is if there's a very large rain event, for example, sometimes flow is diverted in wastewater treatment plants, so they actually don't treat it, it just goes pumped straight out into the environment. But we need to be aware of if that happens so that we can account for that in our numbers. But yeah, hopefully, again, that answers the question.
Thank you very much. Now, are participating laboratories required to use a predetermined analytical method, or do they develop their own?
All our labs have their own methods. We have some suggested methods that we, as a group, all use, and they tend to be, like I said, all very, very similar actually in terms of we tend to use OASIS MCX or HLB, and then we use triple quads or high-res instrumentation. But generally, no, anyone can develop their own methods. That's why we have the intercalibration, the ring test, is to try and check a lab's ability to generate correct data. So we're working with a lot of labs that are still working on their methods, and so we will send them sample, and they will measure the results and return the results, and we tell them how they're going. Are they correct? Are they accurate? Are they, is their variance too great, or that kind of thing? So certainly we're open to suggestion. People can have their own methods, but we encourage a set of methods that we use most often.
Great. Now, we've had an inquiry from an audience member who would like to take part in the group from Portugal. Could you just remind everyone listening how people could go about becoming involved in the work that you're doing?
Yeah, I'll just go back. What I'll do, sorry, just 2 seconds. I'm just browsing through the thing. I'm just pushing the slide here. The SCORE Network website. If you go to SCORE, the website is at the top of the screen now, score-cost.eu. There's a contact button in there. Click that contact and just send a question or an email. That will go to the person that responds to that at the moment is Eric Emke in KWR in the Netherlands. But they will forward you to whoever your local is, your most local contact, or sort of initiate contact from there on. But yes, absolutely, please. If you'd like to take part, then go to the website, make contact with us, and then we'll get back to you.
And following on from that previous question, we have another question here. Do you need to be part of a research institute to be part of COST, or can small and medium enterprises working in the environmental field join in as well?
I believe it's open. You don't have to be a research institute. COST is about creating or increasing communication and collaboration in science and technology. So the goal is actually to bring new people on board and new people. That's what we're there for, is to try and encourage cooperation. I mean, part of this was to try and bring in epidemiologists, public health officials into it. Because at the moment there's too many, well, not too many, most of our group is environmental research institutes, but we would like others to be part of it. So we have a wider framework, sort of wider interest group. So absolutely, it's open to everyone, really.
Thank you very much. Now, just to remind everyone that any unanswered questions from today's session will be answered via email when this session is finished, but we would like to wrap up with one final audience question. And that question is, what type of system flow and mobile phase composition is used for at-column dilution?
That column dilution system that I'm using, the mobile phase and gradient is the same as you would for a standard system. There's no difference. All I'm doing is moving where the mixing takes place. There's literally, I use exactly the same mobile phases. There's no change. I use my aqueous mobile phase is water with formic acid in most cases, and my organic mobile phase is methanol or acetonitrile, for example, often with formic acid, or maybe we have some buffer in there as well. But generally, you don't need to change whatever your standard system is. You just keep it exactly the same. You just move where the mixing takes place. What you do need to be aware of is that it takes, if you're starting your gradient, for example, at only 2% organic, 2% organic, the flow of the organic side of the system is quite slow compared to the aqueous. So it actually can take a little bit longer to load the column. That is very difficult to explain without diagrams. I probably should have included some of those. But the only thing you need to be aware of is that you need to allow time for your loop to be loaded onto the column, and that does take longer, because not all of the flow from the LC system, so if your total flow of your LC system is 1 milliminute, only part of that 1 milliminute is accounted for by the organic phase, say 10%. So then that means it's only 100 microliters a minute, and that may take longer to flush the loop out than it would have done if you had the full 1 milliminute going through. That's probably clear as mud to most people, but if you have questions, just ask, and I can always try and do some more drawings and explain it to you in future. Please just send me an email.
Well, Malcolm, thank you very much. We really appreciate your time and insight. Now, this presentation will be made available for on-demand review and will be available on the website in 24 hours' time. If you have any additional questions, please use the portal to submit these and we will pass these on to Malcolm to answer. Thank you again for your participation. We hope you can join us next week for our next e-learning session. Thank you very much and enjoy the rest of your day.